Okay, this video is on parts of similar triangles, and we're going to take a look at a couple of theorems that we're going to use to solve some more problems involving similar triangles. So the first theorem says if two triangles are similar, then their perimeters, medians, altitudes, and angle bisectors are proportional to the measures of the corresponding sides. So we've already gotten used to solving different problems where we use corresponding sides to set up a proportion. Well, now we're just going to be doing that same thing, except we're also going to be using these parts of similar triangles. In other words, not just corresponding sides, but perimeters, medians, altitudes, and angle bisectors. So let's take a look at some examples of that. So example number one, I'm told these two triangles are similar, ABC, triangle ABC and triangle DEF, and I'm asked to find the perimeter of triangle ABC. Well, I don't have the lengths of all three of the sides of triangle ABC, so I'm going to have to do something before I can't just add up those sides. I do, however, have the lengths of the sides of all three of the sides of triangle DEF, and since these two triangles are similar, I know that their corresponding sides are going to be proportional. So one thing I could do is I could use this ratio here, and I could find the length of this side. I could set up a proportion using this side length here. I could find this side, and I could find this side, and then I could add them all up. But what I'm going to do instead is I'm going to use this theorem that I just learned, which tells me that if I have two similar triangles, their perimeters are proportional to the measures of their corresponding sides. So let me start out by finding the perimeter of triangle DEF. So the perimeter of triangle DEF, I just need to add up the three sides. So 10 plus 19 equals 10, 20, 39. So I know the perimeter of triangle DEF. Also, according to my theorem, I know that the perimeters of these two triangles are proportional to the measures of their corresponding sides. Well, I've got a pair of corresponding sides here with each one of them, with the measure of each one of them. So if my perimeters are proportional to the measures of these corresponding sides, then 16 to 10, that's going to be proportional to the perimeter of triangle ABC over the perimeter of triangle DEF. Well, I know what the perimeter of triangle DEF is. I just found that. That's 39. So I can write this as 16 over 10 equals perimeter of triangle ABC over 39. Now I just need to cross multiply 10 times the perimeter of triangle ABC equals 16 times 39. And 16 times 39 is 624. So I have 10 times perimeter of triangle ABC equals 624. I divide both sides by 10, and I have the perimeter of triangle ABC equals 62.4. Let's take a look at example number 2. So I'm told that these two triangles are similar, and I also know from the theorem that I just learned that if two triangles are similar, then their medians are proportional to the measures of the corresponding sides. And I see I have measures here, or rather I have algebraic expressions for the median of this triangle and the median of this triangle. I know it's a median because it's a line segment drawn from the vertex to the midpoint of the opposite side. So in each one of these, it's drawn from the vertex to the midpoint of the opposite side. So, since I know that the medians are going to be proportional, then I'm going to set up a proportion using the corresponding sides, these two corresponding sides here, of these two triangles. So, 24 to 15 is going to be equal to the ratio of the medians, x minus 6. So now I can cross multiply. 15x equals 24x minus 24 times 6, 24 minus 144. And let's see if I subtract 24x from both sides. And that's going to give me negative 144 and negative 9x. Divide both sides by 9. And I get, oops, I want to divide both sides by negative 9. And that's going to give me x equals 144 divided by 9, which is 16. And now you can also see example number 3 in your notes is very similar to this one. I'm going to leave example 3 for you to solve on your own. In fact, if you want to pause the video now, you can go ahead and try that one before you go on to the next example. Okay, example number 4. Here, once again, I'm told that these two triangles are similar. And I see on these triangles, I have now an altitude labeled on each triangle. I know it's an altitude because it's a line segment that goes from the vertex of the triangle and it's perpendicular to the opposite side. So I have two altitudes here. Once again, I can use my theorem that tells me that for two similar triangles, the altitudes are proportional to the measures of corresponding sides. Well, here are two corresponding sides. Here are my two altitudes. All I need to do is set up a proportion. So 25 over 16 equals 18 over x. And I can cross multiply and I can solve for x. 25x equals 16 times 18. What's 16 times 18? 288. Divide both sides by 25. And that gives me x equals 288 divided by 25, which comes out to 11.52. And again, example number 5 in your notes is again very similar to this one. It involves the altitudes and setting up a proportion using corresponding sides. So I'm going to let you do example number 5 on your own. Again, if you want to pause the video here to do example number 5. And now we go on to the second of our two theorems for this video. This is called the angle bisector theorem. The angle bisector theorem says an angle bisector in a triangle separates the opposite side into segments that have the same ratio as the other two sides of the triangle. So let's take a look at what this angle bisector theorem means using an actual triangle. So here I've got triangle ABC, and I've drawn in here an angle bisector going from vertex B to the opposite side. So according to this theorem, this angle bisector separates this opposite side into segments. So here's one segment, and here's another segment. This angle bisector separates side AC into these two segments, and these two segments have the same ratio as the other two sides of the triangle. In other words, this side, AB, and this side, BC. So specifically what it's saying is that if these two sides here have the same ratio as the other two sides of the triangle, it's saying that side AD and side CD, they have the same ratio as AB and BC. This angle bisector separates this opposite side into segments that have the same ratio, AD to CD, as the other two sides of the triangle, AB and BC. So let's take a look at how we would use this theorem to solve the problem. Example number 6. So here I have a single triangle, and I have an angle bisector. I know it's an angle bisector because I've got two congruent angles here. And according to my theorem, this angle bisector separates this side into segments that have the same ratio as the other two sides. So all I need to do is set up my proportion using these two ratios. So x over 12, that's the same ratio as 9 over 15. And I can cross multiply and solve this for x. 15x equals 9 times 12. 9 times 12, which is 108. Divide both sides by 15. And 108 divided by 15 is 7.2. Example number 7. Again, it's the same type of situation. I have a triangle and I have an angle bisector. And again, this angle bisector separates the opposite side into two segments that have the same ratio as the other two sides of the triangle. I'm going to leave example number 7 for you to do, and we will take a look at that example and also the other two examples that you worked on tomorrow in class.